Welcome. This is the third video in this series on principles of radiographic exposure. In the last video, we explored electromagnetism, explained what ionizing is, discussed radiation including electromagnetic and particulate, as well as different sources, and talked about X-ray production. In this video, we will have an introduction to technique, learn about the emission spectrum, and discuss beam propagation. If you haven't watched the previous videos, I recommend you do before watching this one. We'll begin with an introduction to technique. We'll begin with an introduction to voltage. Two of the parameters of the exposure that can be set on the console when performing a radiograph are the voltage and the amperage. Voltage is the potential difference from one point to the other. The difference is created by one point being charged more positive or negative than the other charge. A negative charge would be created by an increase in the amount of electrons on an object. A positive charge would be just the lack of electrons. We can create this with the introduction of electricity. Electricity is a complex subject and will be further explored in later classes, but for now, the greater the difference in charge between 2 points, the greater the voltage will be. Okay, so the greater that the difference between one being negatively charged and relatively the other one being a positive or being positively charged, the difference in these two, the greater the difference is between the 2 points, the greater the voltage will be. Okay, and the voltage is potential difference. In radiology, the 2 points of interest are the cathode and the target spot of the anode. Okay, so the cathode is negatively charged and the anode would be positively charged. And we employ kilo, which is 10 to the 3 or 1,000 volts on the console. It's labeled as kVp, which is read as kilovolts peak. The other parameter that we can set is the amperage. Amperage is the movement of electrical charge from one point to another. So amperage is the movement of electrical charge. When one point is negatively charged and another is positive or just less negative, the two charges will be attracted towards each other. This will cause the charges to flow from the negative to the positive. So the electrons is the flow, and the electrons are negative, so it will come from the negative to the positive. The greater the flow, the greater the amperage. The more electrons that are flowing, the higher the amperage. In radiology, the electrons flow from the cathode to the anode, which the cathode's negative and the anode's positive. As we said, we employ milli, which is 10 to the negative 3, or 1,000th, okay, of an amp. On the console, it's labeled as MA. This is set as milliamps. We'll bring voltage and amperage together. It should be obvious that the potential difference and electrical flow are interrelated. There must be a potential difference between the 2 points in order for there to be a flow of electrical charges. So there has to be a voltage between 2 points in order for there to be an amperage between the 2 points. In order to complete the concept, we'll use a water analog. Here, voltage is pressure. Okay, so we have water in this bin here, or bucket, and then there's a pipe running. Okay, so there's a pressure, so there's a voltage here where there's pressure through this pipe. Okay, but there's no flow, so there's no current. The water's not flowing, but there is a voltage. Now we release this valve here, so there is a flow of water. So there's a voltage because there's pressure going through this pipe still. There's water pressure here, and there's also a current. All right, so this would be like the flow of electricity. The other parameter is time. Okay, so that's another factor that can be set on the console. Time is measured in seconds, is the base unit of time. Time, kVp, MA, and distance are the primary factors in an exposure. Time is the amount of time the exposure will occur for, so how long the exposure will take. In radiology, the time and the MA are combined into a factor that's called mass. So we can combine MA and time, and we refer to it as mass, which is milliamperage seconds. The greater the mass, the greater the exposure. So the combination of KVP and mass is referred to as technique, and we'll say that's the technique of the exposure. Okay, what technique did you use on that exposure? It's common vernacular, what will be said. The KVP controls the energy, the penetration of the produced X-ray beam. Okay, so that's the quality. So the KVP is the main controller of the quality of the beam. Typical values utilized are between 40 and 120 KVP. The mass controls the amount of X-rays produced. Okay, so mass only controls the quantity of the X-rays produced, how many are produced. And typical values for mass in an exposure might be 0.8 to 500, 3, 4, 500 you could use. Okay. So a little more on mass. Mass is calculated by the multiplication of time in MA. Example, an exposure of 500 MA at 0.2 seconds. Okay, so if we use 500 MA in 0.2 seconds, we're going to get 100 mass. So we just multiply the two together. Okay, so 0.2 seconds is the same as 200 milliseconds. All right, and if we multiply 0.2 times 500, we're going to get 100 mass. Or we could also use 1000 MA in 0.1 seconds, all right, which would be like 100 milliseconds, 0.1 seconds, and we're going to get 100 mass also. Or we could use 250 MA, or 0.4 seconds, which is going to equal also 100 mass. Okay, so all these are going to be the same amount of X-rays produced in the exposure overall. Okay, the difference is how long the exposure is taking. Okay, and we can adjust how long the exposure is taking by changing the MA station. All right, so there may be reasons why you want a longer exposure. Typically, we will want to keep the time as low as possible. We want to keep that time as low as possible because of patient movement, right? We want to capture the patient in that moment, whether we're doing the abdomen, for bowel, there could be bowel movements, so we want to capture it as quick as we can, or if we're just doing general extremities or something, the patient's in pain, we don't want to keep them there that long, okay? We want them to get in that position, we want to make the exposure very quickly, and then we can move on to the next thing we're doing. But sometimes we might want a longer exposure. So a reason you may have already thought, you may already know, that we may want a longer exposure might be for a breathing technique, for like a T-spine. Okay, so for that, we would want to, if we wanted to use 100 mass for this, and we wanted 2 seconds for the exposure time, we would find 2 here, 100, we could divide 100 by 2. All right, we could bring the 2 to the other side, and we could find that we need to use 50 MA, because 50 MA times 2 is going to equal 100. Okay, if we wanted our exposure to be 100 mass, and we wanted 2 seconds, then we'll know that we need the MA station to be 50. Okay, so this can be useful to know to accomplish what you want. As can be seen, the same mass can be attained different ways, okay, which can be used in different ways, okay, that we just discussed. So to give you some practice with maths and finding these values here, you can try these examples. You can pause the video for a second, and you can write these down and try them. Even if you already know it, just go ahead, give it a try. And then the answers will be at the end of the video, okay? We'll move on and we'll talk about the emission spectrum now. We learned that there's 2 different types of X-ray production, characteristic and Bremsstrahlung. Okay, so the characteristic spectrum, when the beam is produced, there are 2 types of target interactions that take place. Target is dependent, which is characteristic of the target element. Okay, so it depends what the target element's made from. We learned that in the last video. Characteristic X-rays are at discrete energies. The emission spectrum is at certain energy levels and nowhere else. Okay, so the emission spectrum of characteristic X-rays is at certain energy levels and at nowhere else. And this is a picture of it. Okay, so we know that the K energies, when the K shell gets knocked out, okay, and an upper shell electron replaces it, and the photon gets produced in that interaction there, and those events, these are the energies of the K shell, L shell, and then so on and so forth. The K shell is the only shell that we're interested in, right? Okay, and we draw that out with a peak. For the full X-ray emission spectrum, we draw a peak at 69 to represent that. Okay. The Brimschaling spectrum. Brimschaling is dependent on the incident electron energy and the angle of deflection of the electron. Okay, if you're not familiar with these things, I recommend you review the previous video. Brimschaling X-rays are continuous. The emission spectrum is at all energy levels up to the kVp of the exposure. All right, so the Brimschaling X-rays here, you can see is a continuous spectrum, okay? And it's going to be all the way up to the kVp that's set, all right, which may be 90 here, all right? There's no point where it's not. The Brimschaling peak is shifted to the left, okay, and then it falls off as it goes higher, because only the most energetic electrons initially are going to be able to create these high energies, okay, and then that electron is going to lose the energy. It's going to release the photon. A photon is going to be produced, I should say, and then that electron is going to go on, but it's going to have less energy, so it can only produce now lower energies, okay, and it can keep producing lower energy photons. All right, so most of the energy is going to be, most of the X-rays are going to be produced at a lower energy. Okay, so the peak is shifted here. Okay, where it's somewhere maybe around about 30 in this, where the kVp is set at 90. About. Since the X-rays are a combination of Brimschaling and characteristic X-rays, there is a combination of both. Brimschaling occurs in greater numbers than characteristic, therefore the curve of the emission spectrum is highly composed of Brimschaling radiation. They say something like 85% of the primary beam is Brimschaling radiation. The other part of the characteristic spectrum of interest is the K-shell X-rays. As we discussed, these energies are represented by a single impulse at 69 kVp. Okay, and we can see the full emission spectrum here. All right, where the Brimschaling is continuous. The characteristic X-rays is represented at 69 keV. The curved peak is shifted to the lower end, as we discussed, with a parabolic fall off after the peak. Okay, so it falls off quickly. Okay, it's not just like a linear fall off. Okay, a straight line. It falls off quickly. Okay, to the peak. After the peak. The maximum energy of the kVp is set. Maximum energy is the kVp that's set during the exposure. So in this exposure, a kVp of probably about 90, 80, probably 90 was set, we'll say, on this graph down here. The characteristic peak is a significant number of X-rays. However, it's only at one energy. How we represent it. Okay, it's only at 69. Okay, those are the only ones of interest. All these lower peaks that were in here, they just get added to this Brimschaling. Okay, all right, and the really low energies aren't of use to the final image. Okay, so we do a thing and we filter those out. We use a filter. kVp is what is set on the console, and then keV is the energy of the X-ray. So you see that this is keV. All right. kVp is what we said. We put a certain amount of voltage, an amperage, certain amount of electricity into the exposure, and then what's produced are photons, which are measured in keV. If the kVp is set below 69, okay, or 70 really, if the kVp is set below 70, there is no characteristic peak. Okay, characteristic X-rays that are useful, which is the K shell, can't be produced, okay, because the electrons don't have enough energy to knock to break the binding energy of those K shell electrons. So there will be no characteristic peak, okay, if the exposure is below 70. Exposure factors. If the exposure factors is changed, the emission spectrum of the beam will change. So we'll go ahead and we'll see from that typical emission spectrum graph how the exposure factors will change. And we know what the exposure factors are, the KVP and mass, right? And we call that KVP controls the quantity, which is the amount, and the quality. Okay, so KVP is the only controller of the quality, the energy, all right, of the X-ray. But it also has effects on. It also has an effect on the quantity, the amount of X-rays produced, and we'll see how that happens here. Mass controls only the quantity. Okay, so mass only changes the quantity. Okay, well, KVP can change the quantity and the quality. So keep that in mind here. So a change in mass has a direct linear relationship to the amount of radiation that is produced. Okay, so if we double the mass, we're going to double the amount of X-rays that are produced. Okay, if the mass is raised, the curve will keep the same exact shape. It will just be raised by the same amount, the same factor that the mass is increased. Okay, so if it's doubled, the curve is going to double. If it's halved, okay, so if the mass is lowered by 80%, but half is a good example, okay? If the mass is halved, then it's going to be lowered. Every point on there is going to be half the distance, okay? Half the number of X-rays. So as we can see in this example here, that if 200 MA is used in this graph, we assume that the time is kept constant here, okay? And so the mass would be half of what was originally used, all right? But if in this graph, if the MA is halved, all right, then from 400 to 200, then every point here will just be half the value. It will just be half the number of X-rays produced at every energy, okay? And the exposure is over 70, so there is the characteristic peak here, all right? But the shape is exactly the same, okay? So make a note that the shape is exactly the same here. The KVP is a little more complicated, as the maximum energy of this emission spectrum will be what the KVP was set at. This is the quality, okay? So that's the quality of the beam, it's the energy of the beam. The number of X-rays increase if the KVP is increased, okay? The relationship is summed up in the 15% rule. So where a doubling of the mass will double the amount of X-rays that are produced, an increase of 15% in KVP will double the number of X-rays produced. Okay, so this will increase the quantity. All right, so 15% increase in KVP will double the number of X-rays produced, double the quantity. And a 15% decrease will half the number of X-rays produced. So we can see that KVP is a very strong factor in the exposure. Okay, the original exposure might be at 80 KVP. A new exposure, if we increase by 15%, so we multiply it by 1.15 and increasing 15% is going to be 92 KVP. The max energy of the keV of the photons can be up to 92, and twice as many X-rays will be produced. If the new exposure is at 80, or if the exposure was at 80 and we go down by 15%, we go to 68, okay, and the maximum energy, the keV will be 68. So half as many X-rays will be produced, all right? Let's look at the graph here. We can see it in the graph, all right? So this is exposure at 82. This is exposure at 72. Okay. Note that the KVP is increased and the peak of the curve is shifted to the right. All right, so we said that the KVP affects the quality of the beam. So the quality is the average overall energy that's being produced, okay? So the peak here, instead of being around 25, is now probably around, 30, maybe 35 here. So the average quality of the beam has been increased with an increase in kVp. The average energy of the beam has increased, okay? That's what's important about kVp. Also, the max energy is increased as well as more X-rays are produced. Okay. So the max energy is increased as well as more X-rays are being produced. Okay. So the interesting or something to do here is to see what the difference between these two is. Okay. If you take 82 over 72, you find out that it's 87%, so it's about a 12.2% increase. All right. If they wanted to make it a 15% increase for this example, they could have used 83 here, 82.8. They ran it down to 82, but it's close enough to the 15% rule. All right, for our example. We'll go ahead. We'll talk about beam propagation. So how, once we produce the beam, we have the primary beam coming out. How does it propagate through the air? What's the properties of that? The inverse square law is the main determinant of how many X-rays. So this is where distance comes into play. Okay, as a primary control factors, we set the two at the console, we set the kVp, we set the mass. Okay, and then distance will have the other biggest impact on the actual exposure, the actual how much is gonna eventually reach the IR. Okay, that we can control. All right. If you haven't noticed, the farther away that you are from a light source, the less intense the light is to your eyes. So the farther you get away from a light source, if you have a flashlight very close to your eyeballs, which you probably maybe you shouldn't do, but it's going to be very intense on your eyes. If it's across a long field, it's just going to be a little dot. Okay, so it's not very intense on your eyes, right? This relationship to visual intensity of a light source and distance away from it is summed up by the inverse square law. The inverse square law is that intensity diminishes by a factor of the square of the distance from the source. All right, so it's true of X-rays, and the equation, which is seen below. Okay, so intensity is by the inverse of the square of the distance away from the source Okay, so as you get farther away, it's not just a linear. Okay, it's not just one-to-one. You move twice as far away. It doesn't get half as intense. Okay, we'll see that here. All right, there we go. This diminishing factor of intensity over distance has to do with geometric effects. Okay, we'll talk about the geometry of it here so we get a broader understanding of it. So imagine drawing a sphere around a point source. So we have a source, and that can represent the source of our X-rays. Okay, it can just be a point in space, and we'll draw a sphere around it. Okay, now we'll find the surface area on a section of that sphere. To find the surface area of the sphere, the equation 4 times pi r squared is used. This is the area of a sphere. Now let's say that through that area, 8 waves will travel through it at a distance of 2 from the source. All right, so we're a distance of 2 meters, 2 feet away from the source, let's say, and we'll designate this as A2, the area at 2 away from the source. So the number of waves going through A2 will be 8, an area of A2. Now let's move back to a distance of 4. Let's designate this as A4, the area at 4. So the number of waves passing through A4 is what we need to find. Okay. First, let's find the surface areas for each distance. We'll find A2, all right, so we'll make R, which is like the radius, which was just the distance from the point source at the beginning. We'll make that 2. If we plug it into the equation here and we do 2 to the second power, which is 4 times 4, we have 16 pi will be the surface area that we're interested in for a distance at 2 away, 2 meters, we'll say. Now, if we go to a distance of 4 meters away from the source, all right, we'll have to use 4 for the R. We plug that in. 4 to the second is 16 times 4 is 64. So this surface area is 4 times as large as the surface area here. We still have the 8 waves going through it, but it's 4 times the area it's spread across. All right. The same 8 waves will still pass through a surface area 4 times the area of the original at a distance of 2 meters away. Okay, and now we're 4 meters away. Therefore, at a distance of 4, only 2 waves will be passing through the original amount of area. Okay, so we went from 8 waves going through here, so that could be like the intensity, how much is hitting the surface. All right, and now when we back up to twice the distance, there's only going to be 2 waves hitting the same surface area. Okay, so I think we can see how we're starting to see maybe how the inverse square law works. We will visualize this here. All right, so we'll say that the square will represent our area of 16 pi that we found, right? With the red dots representing waves. So we have 8 dots, so there's 8 waves going through this area, okay? Of the distance of 2 back. Now if we go to the 4 back, okay, we can see that there's 2 waves. Now there's still the 8 waves that's being produced by the source. There's still the same amount of waves being produced by the source, but now it's spread out over a larger area just by moving farther back. So the intensity in this area, if this was our area of interest, like this is our board, right? This is our detector where we're picking up the X-rays, okay? Now there's only 2 rays going through here, so there's a 1/4 as much, okay, going through the same area. And if we half the distance, so we go back this way, it will have 4 times as much, right? So this is a relationship with the inverse square law. If we want to compare 2 intensities at 2 different distances, okay, so we can have any, it could be any distance, right? In here, then we use this equation right here, okay? We take the ratio of the 2 intensities and we set them equal to the ratio of the 2 distances, all right? We should note that we need to set this up in a way, okay, for it to be accurate since it's the inverse, okay? So since I1 is on the top, we need to take the inverse of the distance here, okay? So the D1 is on the bottom, okay? So we need to keep these two. If you're plugging in values here, all right, you need to make sure that they're plugged in correctly, all right? And we need to square the distance. We can see it here as what we were talking about. So we have a point source here, all right? We drew a sphere around it, okay? And the intensity at the surface, okay, is set by this equation here. The intensity at a surface of just 1, at just a distance away, okay, will just be the original I. Okay, so it'll just be the original intensity. Now, if we go back a distance of 2, now we have 4 times the surface area. Okay, we've only doubled the distance, but we've increased the surface area by 4, and the same amount is still being produced. All right, so the intensity here, how much is hitting this, hitting each area, okay, is a 1/4. All right, and this continues on. Beam propagation. So when the X-rays are produced, they travel in all directions. X-rays cannot be focused. That's one of Rankin's rules. The X-rays that travel to the patient is called the primary beam. Okay, so we call the X-rays that are coming out of the collimator the primary beam. The X-rays travel at the speed of light. They interact with molecules in the air, but by a negligible factor. Okay, it's due to the density of air. The way that the beam interacts with matter depends on the energy of the beam. So it depends on the kVp that we set overall. Okay, so the energy of the beam, which is the quality of the beam, and the density of the matter it is interacting with. All right, and this brings us to a point called differential absorption. In our next video, we'll discuss interactions with matter. This is the lead up to it. Okay, so differential absorption, depending on the density of the matter the X-ray beam interacts with, the X-rays will be absorbed, okay, at different rates. Okay, the greater the density of the matter, the more energy the X-ray will deposit in the matter. So the denser an object is, okay, the more energy that the X-ray will give up, okay, and the more likely it will be to be absorbed. And the greater the energy of the kVp, which is the kVp of the X-ray beam, the less likely the X-ray will be to interact with the matter. Okay, so if we set a higher kVp, it's going to be less likely to interact with the matter and be absorbed. It's more likely to go through it and penetrate it. All right. And we refer to this difference in the way that the beam absorbs based on the density of different materials that it's interacting with, or matter that it's interacting with. We call that idea differential absorption. All right. These are the answers to the questions that were earlier, so you can check yourself here. In the next video, we will discuss differential absorption more. We'll also discuss the X-ray beam and interactions with matter.